The crisis in the cosmos. How James Webb is reshaping our understanding of the universe. In the distant reaches of space, far beyond the sight of even our most powerful ground-based telescopes, a quiet revolution is underway, one that could change everything we thought we knew about the universe. Since its launch, the James Webb Space Telescope, JWST, has dazzled astronomers and the public alike with breathtaking images and data of galaxies, stars, and cosmic phenomena from the earliest eras of our universe. But alongside the beauty and wonder, Webb has also delivered something far more disturbing: evidence that our foundational theories about the cosmos may be deeply flawed. A renowned physicist and Nobel Laureate, Dr. Adam Rees, has sounded the alarm. He and other leading minds in cosmology warn that we may be standing on the brink of a scientific upheaval unlike anything since the discovery that the Earth revolves around the Sun. The JWST has unearthed anomalies so vast, so unexplainable, that they threaten to topple the very scaffolding of modern physics. The problem with our universe. A crisis long in the making. It didn't begin with the James Webb Telescope. For decades now, tensions have been building within the world of cosmology. Discrepancies in measurements of the universe's expansion, contradictions between theory and observation, and strange features in the structure of space itself have been accumulating like cracks in an old foundation. At the heart of the storm is the Hubble constant, a number that describes how fast the universe is expanding. Dr. Adam Rees, one of the foremost experts in cosmic expansion and co-recipient of the 2011 Nobel Prize in Physics, has spent years studying distant exploding stars known as Type Ia supernovae. These supernovae act as standard candles, cosmic lighthouses that let scientists precisely measure distances across the cosmos. But Rees's team made a startling discovery. Their measurements showed that the universe is expanding much faster than predicted by models derived from the cosmic microwave background, CMB, the faint glow left over from the Big Bang. This discrepancy, now famously known as the Hubble tension, has grown more dramatic with every new set of observations. Something is off, terribly off. And now, the James Webb Space Telescope is pouring gasoline on the fire. Webb's shocking discoveries. Galaxies that shouldn't exist. The JWST has done more than sharpen our view of the early universe. It has shattered expectations. In its earliest images of deep space, Webb revealed fully formed massive galaxies from a time just 300 to 500 million years after the Big Bang. According to the standard model of cosmology, these galaxies should not exist. The laws of physics as we understand them suggest that the early universe shouldn't have had enough time to form such large and complex structures. These ancient galaxies are too massive, too evolved, and too numerous to be explained by the current lambda CDM model, our prevailing theory that combines dark matter and dark energy in a universe that is expanding from a single point. Worse yet, some galaxies observed by JWST appear to defy redshift expectations, suggesting they might be older than the universe itself. An absurd proposition unless our measurements or our models are fundamentally wrong. Dark energy. A phantom force under fire. To understand the scale of this crisis, we need to revisit one of the biggest mysteries in cosmology. Dark energy. When Adam Rees and his colleagues first discovered in the late 1990s that the expansion of the universe was accelerating, not slowing down, the scientific world was stunned. The cause, it seemed, was an invisible force pushing galaxies apart, a force that became known as dark energy. Dark energy was hypothesized to make up 68% of the total energy content of the universe, acting as a repulsive counterbalance to gravity. Without it, our models made no sense. But here's the catch. Dark energy has never been directly observed. Its existence is inferred solely from the behavior of galaxies and large-scale cosmic structures. Now, Webb's observations are challenging even this. If galaxies formed faster than we expected, and the universe expanded more rapidly in its earliest days than predicted, then dark energy, as currently understood, cannot be the whole story. Perhaps it doesn't even exist at all. We may be facing the end of dark energy as a concept, one of the foundational pillars of modern cosmology. The collapse of the isotropic universe. Things get worse. Another assumption built into the fabric of cosmological theory is isotropy. The idea that the universe looks the same in all directions. This concept, along with homogeneity, forms the cosmological principle, which underpins the equations of general relativity and our understanding of the Big Bang. For decades, the universe appeared to obey this principle. The cosmic microwave background radiation was smooth and uniform. Galaxies seemed evenly distributed. But new data, some from JWST and some from earlier telescopes, is beginning to suggest that this uniformity is an illusion. Evidence is mounting that the universe may not be isotropic after all. Large-scale anomalies, such as the CMB cold spot, suggest regions of space that deviate significantly from the expected uniformity. If isotropy fails, so does the cosmological principle, and with it much of modern cosmology. Parallel universes and quantum clues. As the macrocosm crumbles, attention turns to the microcosm. Nobel Laureate David Gross, one of the founders of string theory and a key figure in understanding quantum chromodynamics, believes the answers lie not in the stars, but in the particles. Gross argues that the early universe, moments after the Big Bang, was a quantum world, ruled not by relativity but by the strange and counterintuitive laws of quantum mechanics. During this epoch, the universe was a primordial soup of quarks and gluons, too hot and dense for atoms or stars to form.
According to Gross, the fundamental disconnect between quantum theory and classical cosmology is the root of our confusion. We are trying to describe a quantum birth with classical mathematics, and it doesn't work. The solution, he believes, lies in a unified theory, perhaps through string theory or another quantum framework yet to be discovered. Such a theory could finally bridge the gap between the small-scale world of particles and the large-scale structure of the universe. Intriguingly, fluctuations in the CMB, the earliest light we can see, may hold quantum fingerprints of the forces at play during the Big Bang. Gross and others believe these quantum remnants could point to undiscovered particles or forces, or even evidence of other universes. Yes, you read that right. Parallel universes. Are we alone in our multiverse? A growing number of physicists now entertain the possibility that our universe is just one of many, a bubble in a larger multiverse. The theory suggests that universe bubbles form and collide in a vast quantum foam, each with its own laws of physics. Some even propose that voids and anomalies like the cold spot may be scars from past collisions with other universes. Though highly speculative, these theories are gaining traction in the face of growing observational contradictions. The multiverse idea is no longer confined to science fiction. It's now a serious scientific hypothesis, albeit one that challenges our ability to observe and verify it directly. Where do we go from here? As it stands, the James Webb Space Telescope has done more than just take beautiful pictures. It has thrown our deepest theories into question. The standard model of cosmology, with its neatly balanced components of dark energy, dark matter, and isotropic expanding universe, may be a useful illusion, but not the ultimate truth. Dr. Adam Rees, ever calm in the storm, embraces this chaos. This is how science advances, he says, through surprises, through contradiction, through crisis. He may be right. Crises force breakthroughs. They crack open closed systems. They demand new ideas, new physics, and new imagination. We are now witnesses to a revolution, a slow, uncertain, but exhilarating rewriting of our cosmic story. The tools we once trusted are now being recalibrated. The rules we relied on are under review. And the universe, vast and unknowable, is once again reminding us of our place within it. Curious, small, and just getting started.